Okay. Ladies and gentlemen, I think in the interest of time we will start. Okay, but I will try to start slowly so that I know that not everybody is here. Just to review things a little bit where we are with that. So maybe anybody has questions? Yes?
How much power is enough?
How power much is enough? Good question. Well, this is something is actually your decision, right? So it's essentially a probability of detecting the true difference, right? So how often do you want to do that, right? So what's the percentage of true positives you want to have in your experiment? So usually when we do sample size planning, we set it to 80%, but you, that's right. But you can, it's up to you. Clearly higher power means large sample size, right? So it's a bit of a trade-off. So this is somewhat cultural, right? So different areas set it up. So we tend to have the default of 5% false positive rate or false discovery rate, and then 80% power. Mm-hmm.
So if you're doing a pilot study, do you make the initial assumption that your sample variance is dependent on the assay variance?
Sample variance depends on your assay variance. What do you mean?
Like, so let's just say that you're doing a pilot study, you don't know how many samples you're
correct, yeah.
Study. And so I think you mentioned that power is equal to square root of...
No, power is the probability of detecting the true change. Let's see where I have it. Power is the area under the curve. So power is probability, right? So it's probability of finding the change when it actually is present, right? But the power is determined by the sample size, and it is determined by the variability in the biological system. And by the way, I haven't talked yet about the multiple proteins, but clearly different proteins have different variability, right? So here I'm kind of ignoring all of that, right? And I just say representative proteins. So usually what you would do, even if you plan pilot experiments, if you have some historical data from a similar biological organism and similar technology, you would use that across all the proteins, and typically we would take like 75th quantile of all the variances to be on the conservative side, or maybe 80th quantile. And in fact, what I'll tell you up front, so what I would like to talk about later is our tools that we use, that we develop, and what we do is every time we analyze a data set, we immediately treat it as a pilot experiment for something else. So we provide sample size calculations for the follow-up right away. Okay, so that's what we talked about. So, oh yes?
Yeah, so is there a way, statistical test that would show no differences?
No. Because absence of evidence is not evidence of absence, right? So, okay. So if you don't see the evidence for the difference, it doesn't mean that there is no difference, right? It may mean that your study doesn't have enough sample size to see the difference, right? And as we have very well seen here, right, like in this, oops, where was I? Right? So here you only have 186 out of 1,000 instances which actually find some change, right? But the change is very well present because it's a simulated study. But the majority of simulated instances didn't find the change because the sample size was too small. So if your sample size is small, doesn't mean that the difference is not there. And by the way, the true regulation can be, I don't know, like fold change of 1.00001, you know? So technically, it's a regulation, right? Practically, are you interested in that? Probably not, right? So there's that as well, right? So not every fold change is worth really fighting for, you know? Okay, so that's what we do. Oh, yes, please.
I have one.
Mm-hmm.
You might be actually about to talk about it, but how do we account for multiple hypothesis testing when we're doing a large targeted protein mix?
Hold that thought. That's coming up. Okay, so several slides down the road, then let's come back to that. This is actually exactly what I talk about here, right? So what we were saying is that if we look hard enough, we always find something, right? And so in the context of hypothesis testing, it means what? If we have 1,000 hypotheses to test and we have 5% false positives, right? So 5% out of 1,000 false positives we will see, right? Just even if everything is done right, and even if there is no problem in the analysis. So is it okay to have 5% false positives? Well, maybe. It depends, right? It depends a little bit on how you want to study. You proceed with your experiment. So let me just give you an illustration of that. So let's say we have only 2 proteins, so not 1,000, but just 2 proteins. And we do exactly the same thing for each protein. So here is a protein 1, so we have this probability distribution. I just flipped it, right? So we assign 5% probability of false positives in each tail. If our signal-to-noise ratio is in this tail area, we reject the null hypothesis, right? And we do it regardless of what happens for protein 2. So for any possible value of protein 2, we always reject the null hypothesis. So this area plus this area is, say, 5%. Now, protein 2, the same thing. So we have our reference distribution. We assign 5% error here and here, and we reject the null hypothesis regardless of what happens with protein 1. So this plus this is also 5%. But in fact, our experiment has both proteins. It doesn't have one or the other. So our decision is actually this. And so our probability to make at least one false positive, it's actually the combined area here, which is more than 5%, right? So probability of finding at least one false positive increased by having more proteins. And essentially, if you have enough proteins, probability of making at least one false positive is essentially 1. So we're guaranteed to have some false positives. And oftentimes, we're actually interested to know what is the probability of finding at least one false positive difference. And so if we want now to control this combined area to 5%, well, what we need to do, we need to make it smaller, right? And so what you would do is to essentially have this dashed line such that the area outside of the dashed line is 5%. Now you control the joint probability of making at least one false positive decision in the space of both proteins. But it means what? It means that the individual tests are more conservative, right? So now it requires stronger evidence of differential abundance to reject null hypothesis for each individual protein. And so that's kind of what happens. So if you're familiar with Bonferroni approaches for multiple testing, this is exactly what they do. So it's the most kind of the approach which makes fewer assumptions. But it's also very conservative. So what you do, if you want to have 5% of false positives, you divide this by the number of comparisons, right? So if you have 5 comparisons, it becomes 0.01, right? Your cutoff. But if you have 1,000 comparisons, your alpha becomes very, very small, right? And so essentially what it means is that this dashed line moves so far in the tails that it requires an extremely strong evidence to claim any differences. And it kind of makes sense because the best way not to make any false positives is not to find anything. And that's kind of what it works towards. But that's not why we're doing the experiment, right? And so this is not very satisfactory. So Bonferroni approaches in particular, they are not very good because they don't scale to many proteins. If you have 2 proteins and that's all you do, go for it, right? But if you have even like a couple hundred, I don't think that this is an appropriate procedure. But the problem is not even as much with the procedure, but with the criteria. So they say they want to control the probability of making at least one false positive. Now, in our experiments, when we scale them to so many proteins, we probably are okay to have some false positives, just not too many, right? We want to control how many false positives we make. And in 1995, it was a seminal paper by Benjamin and Hochberg, which essentially said, you know, one way to do it is to change our algorithms, how we control these probabilities. But the other way to go is to change the criteria. And instead of saying we want to have very small probability of at least one false positive, fine, we will have some false positives. But let's control the proportion of false positives. And this is what false discovery rate is, right? So this was the table that they reported, and this is the standard notation from this paper, which people kind of keep. So this is, the rows are the truth. This is the true proteins that do not change in abundance or change in abundance. And this is our decision. How many proteins we claim are not differentially abundant, and how many we claim are differentially abundant. Now, the problem with this table is, again, that nothing is observable inside because we don't know the truth. The only thing we observe is R, is how many we claim are differentially abundant. And so Bonferroni, this family-wise error rate, they want to control the probability that V, which is a false positive, is anything except 0 with a very small probability. And this is very conservative. False discovery rate says we're fine with having V being 1, 2, 3, 4, whatever, provided that we control the proportion of V in the total number of rejections. And there's some technicality to avoid dividing by 0. And so, again, false discovery rate is just like a confidence intervals and other things, it's a procedure. So just like with hypothesis testing and confidence intervals, there's a procedure we use to analyze our data. There is also a procedure to adjust our p-values, to transform the p-values such that if you keep collecting the data and using the same procedure, on average, the proportion of false positives among claim changes will be as specified. So typically you would say, for example, 10%. So it's a procedure which says you collect the data set, you analyze it, you do something. Next time you collect the data set, you analyze it, you use the same procedure, and so on. On average, over all these data sets, your proportion of false positives will be controlled at the level as specified. So unfortunately, I don't have time to go into that, but essentially it's a transformation of p-values. And your p-values are essentially made larger, right? So that now it requires stronger evidence to claim that the change is significant. And so what people do to summarize the results, and that's what we do in our tools, is what it's called the volcano plot. Here we have log fold change, and now the or fold change on the original scale, whatever is more valuable to you. And the y-axis is p-values adjusted to control for false discovery rate. And usually we take log to focus on small p-values and negative so that higher values correspond to significance. And so now you can have the horizontal cutoff controls false discovery rate in the list of the adjusted p-values. You can also add vertical cutoffs to control, to add essentially additional fold change cutoffs if you would like. We call them practical cutoffs. And it's totally fine to have fold change cutoffs, provided that they're accompanied with a statistical significance cutoff. And then what you're interested in is the top left and top right corner. And each dot here is a protein, right? So for each protein you have a result. So this is what you would do. Does it make sense?
Yeah, but could you direct me, I mean, if I were to actually do this,
Mm-hmm.
can you direct me to a resource or something?
Hands-on after this hour.
Okay.
Yeah, but it's very easy. So the hands-on session led by Lindsay there in the back, so it will be using R. And in R, this is a one-liner. So it's very easy to do. But in MS Stats, it's done already automatically, so I just for that.
What's the appropriate fold change to use? I mean, some people use fold change of 2, some people fold change of 1.65.
This is now practical significance, so which fold changes would you be interested in to follow up on or report? Depending on your organism, you know, for some organisms or some stresses, you expect really large regulation, so you only focus on those. In other conditions, maybe very small fold changes are meaningful, right? So it's very specific to the experiment, and it's really fine. So my advice is to set it up before you start doing the analysis so that it's part of your protocol. But it's totally your decision, provided that it's not the only cutoff, but you also use the horizontal cutoff based on the p-value. But that's really subject to kind of your decision. Okay, and this is actually something that now I really would like to finish with this part. Multiple testing is important, obviously, right? And it affects our decisions and so on. But I have someone telling me once, okay, you know, this false discovery rate adjustment or multiple testing adjustment, I don't really like it. It didn't work for me because we had some kind of proteins we knew were supposed to change, and then I did the adjustment for multiple testing, and it didn't give me the right results. Like, okay, so let me just make sure I understand correctly. So what you did was you designed the experiment, you collected the data, you processed the data, so found peaks, identified, quantified, and so on, right? You normalized, you had statistical model, you obtained p-values, you adjusted p-values for multiple testing, didn't work out, and you blame multiple testing? So really, it's a whole process, right, that you need to kind of consider, right, to make sure that, remember in the beginning I said reproducible research, right? So it is the whole process. And so, for example, here again, it's a paper by Jeff Ligg and Roger Peng, also the same statisticians who are publishing this blog. So they essentially say that the p-values are just the tip of the iceberg. So if your p-values are not right, probably there are other things which are going on with that. And so considerations of the entire data analysis workflow are extremely important. And so this is now some examples I just wanted to show you, things which really affect our reproducibility, which are not really mathematical. You cannot really express them in formulas, or even in numbers or anything like that. How you design the protocols. So this was one example, also from Jeff's blog, this antidepressant Paxil. It was a clinical trial designed for some main outcomes. The outcomes didn't show any effect, but while they were running the study, they also measured some other things because they could. So suddenly they started saying, okay, but can I look for some other outcomes? And again, if you look long enough, you will find something, some outcomes showed effect. They started marketing it for these other outcomes. Of course, turned out it was a random association because that's not what the study was designed for. So that was a big failure. Here's another one. This is a publication in Statistics journal. So this was a study where someone was comparing two groups of women at peak and off-peak fertility cycle. And well, arguably that's not an easy kind of groups to define, and people were moving women from one group to another, a lot. So they say, oh no, this looks like off-peak, this is not in-peak. So essentially you can move subjects between your groups enough that they could find that at peak fertility, women are more likely to wear red or pink shirts. So this is to say, again, it was not part of the protocol. So I trust that their t-test was fine, and all of their mathematical steps were fine. So this is not something which is mathematical, right? But this is really the whole protocol and how you design it. And so this is something which is called as researcher degree of freedom. So how much researchers can manipulate their data and make the subjective decisions which lead up to, mathematical steps. And sometimes there is a feeling that if it's not mathematical, it's okay. So let's make sure that we do the t-test right. But I would like to argue strongly that all of these informal things, all of these subjective decisions that lead up to the statistical testing are crucial for reproducible research. And those are very likely, because t-test can be automated, so now it's easier and easier to type of things. But all the decisions that lead up to kind of the mathematics, those are most likely to undermine the reproducibility of research. And so the kind of advice that I have here is to establish a protocol for the entire procedure of design and analysis of the experiment, which you define based on your understanding of the technology, understanding of the biology of the problem, understanding of kind of your prior experience with similar data sets. And you essentially say, okay, this is my scientific question. This is how I translate this into a statistical question, for example, comparing the groups. This is how I'm going to allocate my resources. I will select my samples and allocate my samples to all the steps of data processing and so on. This is how I acquire the data. This is what I will do to quantify the peaks. This is how I will normalize this. This is what I will do in terms of data modeling and analysis. This will be my p-value cutoff. This will be adjustment for multiple testing. This will be the proteins I will follow up on. And only then you start the experiment. And if you define this, so this is essentially your best understanding of the good practice and this type of approaches. And then even if your favorite protein turns out to be outside of the cutoff, so be it, right? Because defining the protocol in advance and not manipulating things so that things look kind of better than your first impression, this really leads to as much reproducible research as possible. And so my kind of takeaways are, just to repeat, define the problem, experimental design, randomization, replication, blocking, follow a predefined design and analysis protocol. So do not alter the design in the process, do not cherry pick data and parameters so that the data come out in the best possible way. Understand and state limitations of things, including p-values. And of course, document all the steps. And we rely on R a lot because in R you can have executable code which is also documented, for example, in Markdown documents. So it's a really comprehensive approach to document all the procedures following, for example, data processing steps in Skyline.
What's the degree of freedom, for example, for t-test?
Oh, yeah. Yeah, I was hoping you will not ask that. Just because it takes a little bit longer to explain. So it essentially tells you how much unexplained variation, how much free data points you have associated with the calculation of this denominator. So essentially, you have this sample variance, you used you calculated the mean, and now you look at the variability around the mean. So even if you have 10 data points, originally only 9 are free to vary. Because if I give you 9 points and the mean of 10 points, you can tell me what the 10th point is, right? Because the last point is defined. The same thing for the group number 2. And so now this degree of freedom is something which defines the width of this reference distribution. So it essentially tells you how many data points you have to begin with versus how many quantities you calculated from this data. And so if you have to calculate a lot of quantities, very few data points are free to vary because you already derived a lot of summaries from this data. So the more data points you have and the fewer summaries you used from the data, the more degrees of freedom you have left. And this is something which is kind of used a lot in different areas of statistics, and this is a concept that statisticians are very familiar with. And so it was a little bit a play on this concept because degrees of freedom is something very mathematical which you need in these formulas. But then they say there's also this researcher degree of freedom when the researcher is free to vary different things which are not accounted for in the formulas. And those are actually extremely important.
So it's a degree of freedom is related to the data points you mentioned?
It's related to how many observations you have. So, for example, if you have one number per protein per person,
Right.
you have 10 people in group 1, 10 people in group 2, you have 8 degrees of freedom total. Because you calculate the mean in group 1, the mean in group 2. So, right? So you have 10, what did I say? Not 8, 20 minus 2, right? 18, right? So you have 10 minus 1 plus 10 minus 1. So 18 total. So I'm trying not to make it too technical for you, but there is a concept which defines the student distribution. Now, switching gears a little bit. What we talked about so far was just general, essentially, statistical methodology, right? And I would make very simple assumptions. Let's say we have one number per protein per person, right? And let's say we have one protein and so on. So it's good to set things up, but it's really not what our experiments look like, right? We have very different types of experiments. And so in research in my group focuses on developing methods which are really customized to mass spectrometry experiments that we talk about here. And the big effort in the group is the development of MS Stats. So this is a software package for the analysis of quantitative mass spectrometric experiments, and I would like to tell you about that. And we have some extensions which are actually quite relevant to this course in terms of assay characterization, so related to what Andy was talking about this morning, and also QC, related to panorama QC that you have looked into. Okay, but let me first tell you about MS Stats. As a motivating example, this was a collaboration long time ago where our colleague was studying 2 breast cancer cell lines. And one was high invasive and the low invasive, and this cell line was exposed to 2 types of oxygen treatment, high invasive and low invasive. And then for each oxygen exposure, there were 2 durations, so 6 hours or 24 hours. And then also, it was a long time ago, so they did sample processing. In this case, it was glycocapture, so they also had 2 replicates of glycocapture, and then multiple technical replicates of mass spectrometry. They didn't really know what was important, so they tried to replicate everything as much as they could. And they had questions which were quite complicated, such as, well, is the difference between normal oxygen and hypoxia in one cell line the same as the difference between oxygen exposure in another cell line? So it was more than just comparing 2 groups, it was more complicated questions. And what she was doing then, she would literally, this was actually a DDA experiment, but it doesn't really matter. So what she was doing, she would literally take some runs which correspond to questions of interest. She would extract a subset of data and do a t-test separately for each peptide. And when we saw that, we said this is not a good way to go because you have a lot more data which are relevant to your experiment, and how can we make the best use out of all the available data? Now, if we take all the data set together, we can have a plot like that. So here the x-axis is the combination of all the conditions. So it's called in statistics, it's called a 3-way factorial design because we have 3 treatments or 3 conditions: cell line, oxygen, and duration. And we have all of these combinations of conditions. This is one protein. Here the lines link the peptide ions of this protein, and the dots are multiple replicates in this condition. And you can see several things. So for example, here the first conditions are low invasive cell line versus high. Clearly the cell line difference is very present, right? So between one and the other cell line there's a strong regulation. But then if we want to know how oxygen exposure affects regulation, it becomes more complicated because the peptides do not necessarily agree between them, and there's also different issues such as missing values. So these are the missing values which we put like that. And our goal was to develop methods which would allow us to address this type of experiments in a comprehensive way to maximize the sensitivity but also the accuracy of the results. And this was one of the motivating examples. And since then, the scope of the project grew quite a bit, and we work currently with DDA, SRM, and DIA experiments. They clearly are different, and the properties of the data are different, but at the same time, the format of the data can be very similar. And we leverage the similarity of the format, but we try to express the differences in quantitative properties of the data. So that's what we have currently. And overall, the package and the methodology is like that. So the purpose is to perform statistical relative quantification of proteins and peptides, essentially what is changing. We can work with arbitrary complex experimental designs, not just two groups, but really complex extensions of the groups, including time course, paired design, and other things. For the moment, we work with experiments which what Brendan calls chromatography-based quantification, DDA, SRM, DIA. We don't have, for example, yet work with TMT, although that's in progress as well. We have some better versions for that. Label-free, for label-based, for the moment, we only work with internal standards, such as for SRM. But again, there are extensions to other types of labeling. And in terms of functionalities, we have data visualization, statistical modeling and inference, and as I mentioned, we treat every data set as a pilot study for something else, and we can use variance components from this data set to plan a subsequent follow-up experiment. And importantly, it is free and open source. It is based, it's written in R, and we make a lot of effort to interface this with data processing tools which exist. So our input would be the output of Skyline, for example. So there is a table which produces a list of proteins with their peptides and their transitions across different runs. And with Skyline, we can work in multiple ways. So we have external tool of Skyline, which does not require you to know any R. And then there is a MSStats format that you can export data from Skyline into MSStats format and continue the analysis in R, and this is what Lindsay will be showing you this afternoon. But we can also do other things. So we have converters from other tools such as MaxQuant, Progenesis. We work very closely with Biognosis, so we can also work with their outputs. And our goal is to be inclusive and provide kind of unified strategy for data analysis regardless of the data processing tool that you want to use. That's the idea. Let me just show you how we look at the data. So this is our schematic data representation. This will be one protein. Now this is very different from one number per subject, right, that we had before. So let's just take a look. This is one protein, and the protein has several things. So here the columns are mass spectrometry runs. And different runs are grouped. For example, if you have technical replicates of the same biological subject, these runs are grouped because they come from the same person, right? And then the next runs come from another person and so on. And then biological replicates are also grouped, for example, by condition, because this set of subjects come from healthy maybe, and this set of subjects come from disease. By the way, we have a convention in MSStats that each biological subject has to have a unique identifier. And we use this to infer the type of experimental design. For example, if the subject here has ID 1 and the subject here also has ID 1, then we know that this is either a time course or a paired design when the same subject gets multiple measurements at different time points. On the other hand, if the identifiers are completely different, then we know that it's a group comparison design. And this is important because the models that we specify will be different depending on which design it is. So we can kind of infer that just from the structure of the data. These are the columns. So the columns reflect the biology of our experiment. But then the rows reflect the technology. The rows are the features. And we say feature kind of interchangeably for peptides and transitions. For example, for SRM, if you have 2 peptides and 3 transitions per peptide, you have 6 features. We don't really distinguish, at least not at this stage, we don't distinguish which transition came from which peptide. And the important thing is that the values in this table are the log intensities of the peaks. We take the log right away. And the important thing is that some of those values are missing, and some of these values can have interferences or outliers and so on. And our job is to deal with all of that and integrate all the information available for this experiment to best look for differences between conditions. And for example, if you want to compare condition 1 versus condition 2, but you have 5 conditions total, it is still advantageous for us to look at all the conditions because we can still have a sense of variability in the data and essentially get the denominator in our signal-to-noise ratio, even if we only want to compare group 1 and group 2. That's the advantage. So we try to analyze all the data from an arbitrary complex design to learn as much as possible about the variability. And this, by the way, technically means that we increase our degrees of freedom by looking at more runs simultaneously. So that's the plan. This is the input itself. This would be the example where even though I show the data in a wide format where runs are in columns, what actually happens in technically, as far as input, it's the data in long format where one row in this table corresponds to one number in this table. So one row is essentially a peak in the data set. And each peak is characterized by the protein, peptide, precursor charge fragment, product charge, label, condition, replicate run intensity. And this is what we call a 10-column format, and most experiments that I just described can be expressed in this 10-column format. And again, in Skyline, you can just export this report out of Skyline. This is the overall workflow that we see in terms of analyzing the data. Well, first of all, experimental design, as I mentioned, you really cannot underestimate this. It's really important. This was the example of design that I just mentioned, but this is another example of design also from one of the collaborations that we had. This was a clinical study of osteosarcoma, so these are childhood cancers. And they had some controls, which they had plasma samples once, but then they had disease subjects which had multiple measurements in time, at diagnosis, at several time points during chemotherapy, before surgery, after surgery, and they also had like longer-term follow-up. Here it's a complex design in that it's a combination of group comparison and a time course experiment. So one group has a time course measurement, the other just has controls. And the questions they asked were, for example, which proteins are different between controls and disease and diagnosis? Among those, which proteins came back to their level comparable with healthy subjects at the end of the treatment versus which proteins did not come back? Which proteins were affected by surgery primarily? And this is a case where you really are best served by analyzing the entire data set together as opposed to extracting different pieces. Mm-hmm.
So the disease, the ones who had cancer, barely had the time course.
Only the disease subjects, yeah.
The
Mm-hmm.
controls didn't have any time
Correct.
course. But how can you then be sure that there is no difference? Because if they're kids, they just grow and then your proteins change basically as well.
Correct. The difficulty was in finding the controls, and I actually don't remember the details. It was a long time ago, but they had very much difficulty having repeated measurements on controls. I think these were kids who were coming for an eye exam or something like that, and they were donating there. And it was very difficult for them to get them to come back repeatedly. Clearly. Now, what I don't know, so I think these are weeks, right? So we're talking between 0 and 14 weeks. It was not that long of a treatment. I agree, and probably what I don't remember is what age and gender matching here and how the age distribution varied. I would argue that this is a limitation of this study for sure, but I would also argue that 14 weeks is probably not too long of a term depends on the age of the kids, right? So how big changes. So this is something that clearly clinicians should give an input, right, on how to create appropriate controls. Most definitely.
Just add one very
Mm-hmm.
So on the topic of, well, this isn't a very long time frame,
Mhm.
so it must not be a big deal.
Mm-hmm.
I work on cardiac aging, and I use a mouse model, and the proteomic, like the overall abundance differences and shifts that you see between 12 months of age for a mouse and 24 months of age are extraordinarily dwarfed by the differences you see between 24 and 26. So having a small or a large time frame is nearly meaningless unless you have some evidence to back up whether or not it's important for your study.
Mm.
So 14 weeks may be meaningless at like 12 years old, but I don't think anybody would argue that at 3 months.
Mm.
So that's...
I must,
Don't look at absolute
I'm the first to admit, I'm not an expert at all in osteosarcoma, right? So I do not know much about that. But as far as the design, I agree entirely that this is where the expert and the actual kind of, subject matter should tell you what are the important factors to account for. And for example, either you really build in controls which also have time course measurements, or you build controls which have enough distribution in age to account for that. Most definitely, yeah. But the good news is that if you have this type of design, and if it's done correctly, we can work with that. So that's, I think, the good part of it. Okay.
As long as we talk to you first, right?
Absolutely. Oh, it's going well.
No, not at all. We're still accepting others as well.
Okay, so let me just continue because I want to make sure that you have everything you need for the hands-on part, right? Because this is really important things now. The next step, once the data are collected, the next step is quality control normalization. And again, it's one of those researcher degree of freedom situations where you can use multiple things and they will very much affect the results, but this is not something which propagates itself directly into the testing necessarily. This is how we would view the data. Here the x-axis is mass spectrometry runs. Now they're not plotted in order of acquisition, but more in order of the groups. Hopefully they're randomized, right, and they're not acquired like that. And here vertical lines separate conditions. In this particular case, it was a time course with 10 time points. And if all you have is a label-free experiment, which has no other standards or nothing else, you would see patterns like that. Here, the boxes are log intensities of everything in this run, across all proteins, all peptides, and so on. And you see that the intensities shift dramatically between runs. But then again, it's a targeted experiment. This is an SRM, and we target proteins for a reason, because we expect them to be changing. Now, is this change biology or is it change a technological artifact? And the fact is that you will not be able to tell without appropriate standards, right, or without appropriate additional steps. Now, in this particular case, it was actually an SRM experiment with labeled reference standards for each endogenous peptide of interest. And in this case, in MS-Stats, we visualize it like that, where the left panel has the reference peptides and the right panel has the endogenous peptides. And now we see that the references are quite a bit more stable. Now, this gives us an indication that this is the biological effect and not the technological effect. And what we do here, just for the purposes of visualization, we would apply a normalization which equalizes all the boxes between the references, because in labeled references we don't expect to see any biology, so we expect them to be constant. Every discrepancy is an artifact of either spiking them in or artifact of quantification, and we apply the same adjustments to the endogenous, and now we see that there is really a shift in time among most proteins. And just to kind of clarify, we can normalize in multiple ways. So this is the standard-based normalization, where we have one or a few standards. So the algorithm would be, again, everything on the log scale, subtract the median of the log feature intensity of the standard from each run, and then add back the median of the median so that we preserve the scale of the measurements. The good thing is that the standards do not have biological variation. They are independent on what type of features we measure, how many proteins. The problems are that they only count for artifacts which occurred after we added the standard, and also if the standard itself is noisy, as Mike was saying earlier, then we actually add more noise than we help, and it may actually introduce more problems. What we advocate is to actually have multiple standards, but not use all of them, but only use, let's say, one, and then treat the other standard as if it was any other protein in the sample, and see how it affects the second protein. If the second protein improved, then it gives you extra confidence that your normalization worked correctly. If the second protein became more noisy or didn't help, then it's an indication that probably your normalization was not very effective. So that's one way to do this. So this is for the standards. And then median normalization, instead of normalizing the, with respect to one standard, we equalize the medians of all the log intensities across all the runs. And this is something which is done, for example, in genomics a lot, especially like in microarray experiments a long time ago. This is tricky because it assumes that the majority of intensities do not change in abundance between conditions. So this can be appropriate, for example, in DIA experiments or even in DDA somewhat. However, it's definitely not appropriate in SRM experiments. So normalization is very experiment specific. But again, my recommendation is to define this protocol before starting to normalize, because otherwise it is very easy just to overfit the data. And the last thing is the quantile normalization, where instead of equalizing the medians, we equalize all the boxes. This normalization we only apply to labeled standards in SRM experiments. We do not apply to endogenous analytes because we think it's too strong and it really removes the signals together with the technological variation. I'm going kind of a little bit quickly in the interest of time, but please stop me if you want me to spend more time on something. Okay? Now, the next thing is statistical modeling. And this is really where the core of the contribution of our methodology and software is. And let me spend a little bit of time on that. But the idea is to use all the information that is relevant to this protein and to this particular study and summarize this in the best possible way. I'll just skip that. Again, going back to the view of our data set, what we would like to do is to write essentially an extension to this two-group approach which we discussed earlier today that characterizes all the contributions of variation. So the intensities of peaks are affected by conditions and by the subjects. So this is the pink part of our experimental design. This is the biology, and this is what we're interested in. And then they're also affected by the features and some additional artifacts. This is the technology. And what we realize is that the variability between the subjects is the biological variability, which is important to us. The variability between features, it reflects the technology rather than biology. And essentially, this type of model can be approached by a two-step procedure, where first we summarize all the features with one number per protein per run, and so we focus on the yellow part, and then we focus on the pink part to reflect already the specific biological aspects of the experimental design. And this is what we do. And there is a more theoretical justification for that, which I would skip, but for practical purposes, what we do, we first summarize all the numbers across all the features in one run, and then we just focus on the pink part. For example, if we have no technical replicate, just one replicate per subject and two groups, we're exactly in the situation of a t-test, which we discussed earlier today, after we summarize all the features into a single number. And now the question is, well, what is a good summary? One way to summarize this is to take the sum of all the intensities of the protein in a run on the original scale and then take a log. This is exactly what Skyline is doing. But we propose something else which we believe works better than just taking the sum of all the intensities on the original scale. And I will show you that. But before I do that, so let me also make another point. We tried, as I mentioned, we tried to be inclusive and not only work with Skyline, but work with different types of data processing tools, which means that in addition to all of that, we also have to account for different types of decisions and different philosophy that different data processing tools may have. And there's, as it turns out, quite a bit of discrepancy between different data processing tools. So here is one example. So this is unfortunately DDA and DIA. I don't have an example with SRM handy, but let me show you anyway. So this is DDA example. If you have seen the paper MaxQuant, the LFQ MaxQuant paper from Jorgen Cox, so they have a control data set where they have 1, 2, 3 mixture. This is this data set from this paper. And here is another data-independent acquisition data set from Biognosis, also in a recent publication in MCP. So what we did, this data set was processed with Skyline, MaxQuant, and Progenesis. And this data set was processed with Skyline and with SpectraNote. And the plots here, what they show is the histograms of log intensities of everything in this data set across all features, all proteins, all runs, put together and just plot log intensity of all of these things. And I hope you see right away that it's the same data, right? So same experimental data set processed by different tools. I hope you see that there is quite a bit of difference between the output of different tools. For example, the range of values. Skyline has values between 20 and 35. Progenesis has values between 10 and 30. Just the scale of the values is different. And it's okay because different tools determine peak integration different ways, right? You can quantify peak by apex, the entire peak, you can truncate the tails. Of course, it will determine the scale of your values, right? It's fine because we want to compare them between conditions. We're not interested in individual values as long as it's consistent. But then there are other things. For example, in Skyline, the vertical line here is the number of zeros. So Skyline has 1,389 zeros. MaxQuant has no zeros. And Progenesis has 600 zeros. On the other hand, Skyline has only 33 missing values, but MaxQuant has 38,000 missing values. And Progenesis has no missing values. Quite different decisions, same data set, very different decisions made by these tools. And the same thing for DIA, right? There's difference between the tools. And essentially what we decided to do is to not take the output of these tools, including Skyline, literally. But we decided to essentially read between the lines and try to understand what these different types of values which are reported actually mean. And what we decided to do is to plot this type of histograms and then say, here's a vertical line, which is dataset and tool specific. And we claim that below this vertical line, we don't trust the values. So call them zeros, call them small numbers, call them NA. We essentially determine they're not trustworthy. So whatever the tool decides to call them, we think we will not be using them. And this line is determined a little bit heuristically, so we look at the quantile on the right tail, and then we flip it symmetrically around the median. It's a heuristic procedure. But now, once we decided that we do not trust these values, we need to decide what we do about that. And the idea is that when these values are small, we essentially say that these peaks have difficulties being quantified because the analytes have low abundance. And they are below the limit of detection. And now we need to handle that. And for example, MaxQuant, Progenesis, and others, they just have this, they don't really distinguish missing for other reasons versus missing flow abundance. Skyline distinguishes that. So when Skyline outputs NA, and this is why there are only few NA, when there is a peak, but the peak cannot be integrated. For example, when there's a large overlap between multiple peaks, or when your transition moved outside of the window, you schedule your transition in some window, but it actually moved out, so you cannot reliably quantify the peak. So then they know that the peak is present, but it's not small. That's NA. But when the peak is almost like hiding in the noise, it will be around zero. For Skyline, NA, we leave them as NA. For every other tool, everything which is either below the vertical line or NA, we treat them essentially as missing because it's low abundant. In a statistical language, missing at some specific abundance is called censoring. And these missing values are different because they're missing in an informative way. They're not just, we don't know what the value is. We say, we don't know the value, but we know it's supposed to be small because the analyte is below the limit of detection. And when you know this extra information, you can do better than just say it's missing. And this is exactly what we do. So now going back to this table, so now first I focus on the yellow part, right, on the technology part. We have some missing values which we leave missing, but others we now claim that these are missing because they're low abundant and they're censored. And there is statistical technology that allows you to work with this type of censored values. The analogy for this, by the way, is in clinical trials when they monitor survival and the patient drops out of the study because the patient survives very well and they just don't come back. So the survival is missing, but you know that the patient did very well. So this is an informative missing. So this kind of came from this type of technologies. And now what we do, we look at this data as a two-way table where some of the values are supposed to be small. And you can use statistical procedure, so essentially specify a two-way analysis of variance, which allows you to say some features have higher ionization than others, some runs have higher values than others, and then some values are missing because they are supposed to be small. And what you can do with these models, you can have a summarization which is doing better because you use missing values in a better way. And then we also do a second round where we treat outliers and we use a robust summarization by Tukey, Mead, and Polish. And after that, we arrive to this data structure which only has one number per protein per run, and then we can use standard statistical techniques to accommodate the experimental design and work with that. So that's really what we do. And then finally, we have the biology part to take care of, and we can extract subsets of conditions. We can have arbitrary linear combinations of conditions. For example, the difference between normoxia and hypoxia in low-invasive cell line, is it the same as the difference between normoxia and hypoxia in high-invasive cell line? And we can compare that. And this is our output in the form of a volcano plot, just as we discussed earlier. Let me just give you some examples of how it works and why it may work better. So this is one, and I apologize again, I have a DDA example here. I don't have an SRM, but you know, in SRM there's less to illustrate because in SRM often data are pretty good quality. DDA examples sometimes are more kind of nicer for us to illustrate the difference. Here we have one protein. It's a spiking experiment, so we know the true change between conditions. This is a background protein, so there's no difference between conditions. The light gray lines, these are the individual peptides of this protein, and the color lines, they're summarizations by different methods. So let me just concentrate on the green one. This is log of sum. This is what Skyline would do. Take the sum of the feature intensities on the original scale, and then take the log. And the other is proposed is the red. So you see that log of sum is above the gray lines, of course, because you take the sum of all the values. And then the proposed approach, it's more generalized average, so it's in the middle of the gray lines. But the point is, you know, oh, and here the horizontal line is this line below which we don't trust the values. And everything is above. So this is a very good protein. There is no problem, right? And when there's no problem, there's no problem. Every method, I have two other methods here, but proposed and log sum, they all perform very well. So all is fine, right? Now here's a situation when we have an outlier with a low intensity features. Log of sum is not really affected. We compare condition 3 to condition 1. Again, it's a background protein, no change. Log of sum is not affected very much because small values, they don't contribute much to the sum. So it doesn't really matter. But then, and the proposed approach works quite well as well. However, if you have an outlier in a high intensity peak, then the sum effect is affected quite a bit. And here again, it's a true-false change of 1, and the estimated fold change by log of sum is 3.5. Clearly, it mistook this artifact by the true change between conditions. But the proposed approach could handle the outliers. Well, in the real life, it's kind of more like that. Oftentimes, we see situations when everything is all over the place. We have some outliers in high-intensity features, some missing values or low-intensity features. So we would say that we don't trust anything below this cutoff. And here we compare condition 1 and 2. The true-false change is 7.5. Log of sum only gives us 1.5. The proposed approach is the closest to the true change because we can take care of these missing values and we can also take care of outliers in high-intensity values. So this is the idea of this summarization, that we can do better than just simple approaches. Okay. And we can extend this to SRM experiments, and you will see this in the hands-on. Last thing, experimental design. As I mentioned before, so we need to get variance components. We get that from our data analysis. We take a quantile, typically 75th quantile, across all the proteins. And we would make plots like that, where the x-axis is the fold change that we're interested in, and the y-axis is the number of replicates per group. Well, first thing is obvious. The smaller the fold change you want to detect, the more replicates you need, right? I think it's quite clear. But then there are other things. Here, the solid line is the situation when you only have one protein in your data set, which is not very realistic. And the two dashed lines correspond to the situation here where half of the proteins are expecting to be changed. And this line corresponds to a situation where only 1% of the proteins is expected to be changed. For example, if you design a SRM experiment, you expect a lot of changes because you select your targets. On the other hand, if you do a DIA experiment, you will quantify many proteins, and you would expect only a small percentage to be changing. Well, it turns out that if you expect more proteins which are not changing, you would need more sample size to compensate for that more opportunity for false positives. Right? So if only a small percentage of things is changing, you have more proteins which are potentially a source of false positives. So you have to work harder to protect yourself against false positives, and it translates into a larger sample size. This is another argument in favor of SRM experiments, because if you know what you want to quantify, you have less multiple testing, your targets are more likely to be changing, so you have less opportunity for false positives. So this is a good thing. Okay, let me just show you a little bit for evaluation, what we did with that. For testing, we have accumulated a large number of spiking experiments. We really like those because you know the truth, and you can see how different methods go about finding the truth. It's not really perfect because we don't have the actual biological variation as part of it, but it gives us some ideas already. So what we do here is, because these are spiking experiments, we break them down by the true fold change. In blue is the background proteins, which are not changing. The rows are different magnitudes of fold changes. And the colors correspond to relative sensitivity and relative specificity. Essentially, darker color is better. It means that it was the most sensitive method or it was the most specific method. And this is the same data set from which I just showed examples before. This column is hypothesis testing using summarization by log of sum. This is the summarization based on the proposed approach. Because of these issues with outliers and missing values, the summarization by MStats performed better. And then we did the same thing across many data processing tools and many data sets. Here we have this data set processed 3 times, this one as well. They're all DDA here, and this one is 4 times. And the leftmost column is the proposed approach, and you see that with some minor exceptions, it's always doing better than log of sum or some other types of summarization that people have. And the same thing for DIA, also with some exceptions, so it does quite well and consistently better than just taking the sum of the intensities on the original scale. And what really makes me happy is this result. We try to understand how different data processing tools impact our ability to find differences when we consistently apply the same data analysis procedure and the same protocol. So here we have the first DDA data set processed with Skyline, Max Quant, and Progenesis, and we see how many of the true changes were detected by all the data processing tools if the downstream analysis is the same. So it's only 11. With the proposed approach, the consensus increased quite a bit between the 3 tools. And it turns out it's a very consistent situation across the board. So this is another data set. Also, the intersection increased, and this is another data set that the intersection increased. So our conclusion is that the downstream processing, if we do it in a kind of more detailed way, we can actually compensate somewhat for differences in decisions that different data processing tools make. So this is one, and the same thing happens for DIA as well. So we increase the overlap between different tools as compared to the log of sum. And MStats, as I mentioned, it's available open source and it's implemented in R. We have a dedicated website on msstats.org, and you have a mailing list, and we have quite a bit of documentation and case studies that you can use as an inspiration for the work. And it's also available in 2 other places. It's available as a Skyline external tool. Oh, I lost the mouse. Okay. It's available as a Skyline external tool. Oh, here. And it's also available through Bioconductor. However, in Bioconductor, usually they limit the release to twice a year, so the daily version of the software is the most up-to-date, so the Bioconductor may be somewhat up-to-date. So if you're familiar with Bioconductor, it's a repository for R-based packages for computational biology research. So MStats is in the top 20% most downloaded packages in Bioconductor. And let's see if we can see this. What I decided to do here, because I know you will spend a lot of time also working with group comparison in Skyline, I wanted to highlight a little bit the similarities and the differences between what Skyline does and what we do. Now, we work very closely with Skyline developers, so there's a lot of similarity because our work is very inspired kind of by experiences on both sides. But there are some differences which may be valuable to you. So first of all, the setup. In R, well, it's a command line, and Lindsay will guide you through just to show how this works. It's probably not as straightforward for some, but the payoff is really high because you can manipulate your data in a lot more ways than when working with graphical user interface, either in MStats, but more generally in R. You can really manipulate and document your data in a lot more ways. So I advocate very much using R when possible. Now, in external tool, Skyline external tool, there's a graphical user interface, so just select it in the menu. Or in the group comparison in Skyline, you have seen already, there is also a menu. Now, for normalization, Skyline offers 9 equalized medians or ratio to heavy. We have other things, so equalized median is the default. Quantile we use for SRM when we work with labeled references, using global standard, and we also have no normalization as an option. Now, summarization, we summarize per run, meaning that if you have technical replicates, we will have one number per mass spectrometry run. Skyline would summarize per subject. If you have technical replicates, the subjects will be summarized. Now, in terms of the summarization, so this is probably one of the bigger differences. So Skyline uses log of the sum of the intensities in a run, but they also have options average log of the sum of the intensities of all technical replicates. And they also implemented the robust procedure, which we use as well now. Our approach is imputation, so treatment of these censored values. This is unique to MStats. Skyline does not do this, in large part because we rely on libraries which are hard to interface with Skyline. So our approach is a combination of imputation of the censored values and robust summarization. We can also do robust alone without imputation, and we can do linear model. It's essentially glorified average, just average-based summarization. External tool has less options. It just uses our default censoring and robust summarization, doesn't use the other. And then after that, hypothesis testing, we use linear mixed models, which allow us to extend this to a variety of designs, including time course, paired design, repeated measurements, and so on. So we really are very flexible in our external tool. In Skyline, it's not really possible to do time course, as far as I understand currently, or paired design. So you really are limited to group comparisons in Skyline. After that, multiple comparisons. So we can look at multiple comparisons of groups, including arbitrary linear combinations of conditions. External tool a little bit less, but quite a bit as well. In Skyline, one comparison at a time, so even less limited. Everybody does corrections for multiple testing and with Benjamin Hochberg. And then for visualization, so in Skyline, well, Skyline does a lot of its own visualizations, obviously, right, which are very good to use. For testing between conditions, Skyline reports log fold changes and confidence intervals for that. So we have more options for visualization, so profile plots, QC plots, condition plots, volcano plots, and so on. And we also, when we have many conditions, for example, in time course experiments, when you look at, compare many conditions in a sequence, we also have a heat map visualization, which shows you, for example, how things progress in time. Okay, so this is really the summary for MS Stats. Do you have any questions on that before I move on to other things?
I was a bit confused when you were detailing how this proposed method outperformed the log sum. But what is the proposed?
That's what I just described. So it's a combination of imputation of censored values and robust summarization. So this is what I was kind of talking about in the slides before, right? So when we have, I don't know what to call it, it's an MS Stats, I guess, method. So what it does first, it removes low values based on this vertical line cutoff. It looks at this two-way table. It summarizes this by contribution of rows and columns while accounting for the fact that missing values are informative and in a way which minimizes the influence of outliers. So this is essentially model-based summarization, which has this properties, as opposed to just taking the values and taking the sum of them in one column. Well, it's more sophisticated statistical procedure, but we hope that there is a benefit for that.
I guess I was just confused because you kept calling it was proposed. I guess it needs a better name.
I agree. Well, let's call it MS Stats. How about that?
Yeah, I get that now, yeah.
Sounds good. Yeah. Okay, so this was, any other questions?
This is very specific to Genesis. So you mentioned that one point that you find no missing values. But I guess for Genesis sometimes it puts zeros sometimes for peaks that are missing. Have you ever seen that?
Well, so, right, so here I think, yeah, so it's
just counting zero as a value.
exactly, so we count zero as a censored, and so we have 1,937 censored values. Yeah, so the only kind of important thing about progenesis is that it doesn't distinguish missing at random from missing at low abundance.
Right.
And because we don't know the difference, we assume that everything is low abundance, because those are more frequent. So with Skyline, if Skyline reports NA, we don't touch it, we leave it as NA. But with other tools, we just don't know, so we treat everything as censored. Okay, let me just show you in the remaining time two extensions that we have recently developed. So these are fairly new developments, and I think that especially for the targeted workflows, my hope is that they will be useful. So the first approach, or a first extension of MS Stats is for assay characterization. So when we develop targeted assays, and we spent quite a bit of time this morning talking about the fact that we need to have a calibration curve where we can relate known quantities to peak intensities so that we can obtain absolute quantification, and that one of the bigger problems with this approach was the assays that are not linear, when they deviate from the linear patterns. And oftentimes it creates a problem, especially if you try to do this in a large scale. If you work with SRM assays, and especially you focus like on a small number of analytes, I guess what you can do, you can fine-tune your concentration in the calibration experiment so that you hit exactly the linear portion of the dynamic range, and you work with that. But more recently, what we try to do is to do it on a larger scale, for example, with DIA experiments. And for those, it's really not feasible to fine-tune the range of concentration separately for each peptide so that they're all exactly linear. So we're bound to have nonlinearity. And this extension that we had kind of hopes to offer solutions for people who do assay calibration and assay characterization in experiments which work with many analytes simultaneously. So as I mentioned earlier, we work with concepts always, right? So what are the concepts here? So we distinguish the canonical calibration curve and apparent calibration curve. The canonical calibration curve essentially says, okay, these are the concentrations, these are the intensities. So first, there is just noise, because the analyte is so low it cannot be detected. At some point, the analyte becomes detectable, it's a straight line. And then at some point, it reaches the saturation limit and it becomes horizontal. this is what we call the expected pattern of intensity, a canonical curve. But the real life is not like that, because in areas which are kind of close to these change points of the canonical calibration curve, it's actually not so easy to say this is noise and then suddenly there is a signal. Oftentimes it's a little bit in between, and so the profiles slowly change to horizontal pattern, right, from the linear pattern. And this is really the area that we see a lot when we work with large-scale experiments. There is this as well, but this is more rarely seen because we don't always have high concentrations. But this is a very big problem. And it turns out that this really undermines our ability to characterize the assays. And this dashed line is what we call the apparent calibration curve. This is where the noise from the background samples interferes with some small signals from the analyte. And our goal is to reflect the apparent calibration curve and help situations where it deviates from linearity. But before we do that, so what we need to do is to define the concepts which we try to work with. We focused on two approaches. One is limit of blank, and the other is limit of detection. And there are multiple definitions, but we work with definitions which are very frequently used in the literature. So let's say we have a straight line, so we just fit a straight line to our data, and we do two things. So first of all, we have the range of the noise. So using blank samples, we determine what is the range of variation from the sample which does not contain the analyte. And this range of noise is actually a prediction interval. So unfortunately, I didn't have time to tell you the difference between the confidence interval and the prediction interval. So prediction interval is based on the standard deviation. So confidence interval is based on the standard error. Prediction interval is based on the standard deviation. It tells you how much variability in the actual population you have. So you're not only just confident in the average, but you're confident. You see what's the range of the possible values in the entire, in all the values. So this is the prediction interval for the blank. And the same thing for the straight line. You can have the confidence interval based on the standard error, and then you have a wider prediction interval which predicts the actual observed values in the increasing kind of linear range. And so now limit of blank is the point where the prediction interval for the noise intersects with the fitted straight line. And limit of detection is when the prediction interval for the blank intersects with the lower bound of the prediction interval for the increasing line. These are actually quite standard definitions that people use, and this is useful because this can be automated in a very nice way. So this essentially tells you, okay, my signal starts getting outside of the noise region. This says that my signal is quantifiable because now even the lower bound of the prediction interval will be outside of the noise region. So these are the two definitions that we will use. Now, the problem is that when we start fitting the straight lines, like here, for example, so often we have concentrations, true concentrations, which are quite large. And if you look at this figure, I'm sure you have seen figures like that, it looks quite reasonable, right, more or less. For example, R square is 0.99, coefficient of correlation is 0.99, right? So you would say, okay, well, I have an assay which is reasonably linear. But then the problem is that if you zoom into very small concentrations, well, you see that it doesn't fit at all. But this is the range which we're really interested in when we want to quantify limits of detection and limits of blank. And oftentimes the problem with these assays is that there's some large concentrations that really dominate the curve, and you really don't realize that you have problems in this particular region. And what we try to do is to focus on this region here. Okay, how do we do it? Oh, by the way, before we do this, so what people do currently if they realize that the fit is not very good, they do a few things. So either they would do some robust fit, which is not affected by outliers, or there is a logistic curve fit, which pretty much follows the apparent calibration curve. But we argue that they don't fit very well because they have a lot of constraints. And here are some examples for this. So everything looks more or less reasonable on the full scale of true concentrations, but then if you zoom in, so straight line clearly doesn't look good, but even the logistic curve fits. They have constants, for example, they don't go through these points very well, and so on. So we argue that there is a lot of constraints. And by the way, if you try to do it on a large scale, if you have a peptide which now is entirely in the linear portion of the dynamic range, logistic fits, they fail because they don't have information on the flex points, and you cannot even fit, you can only fit logistic curve if there is a flex point. So none of the solutions is general enough for all the peptides in your experiment, so it's a problem. What we decided to do is to actually start from the basics and focus on the concept of the canonical calibration curve, which we expect to see if we didn't have noise and interference and so on. We focus on this lower part where we say, okay, this is it's essentially bilinear curve when it's horizontal up to a certain point and then it's an increasing line after this point. But this point is unknown, so it's another parameter that we have together with everything else. So now we have, usually it's two parameters, right? It's intercept and slope, right? And now we have three parameters, intercept here, change point, and then slope here. So one extra parameter, an extra degree of freedom in statistical language. Therefore, the curve is more flexible than just a straight line. But the problem now is that this change point is unknown, and a way to handle this uncertainty in statistics is use resampling. So what we do, we take the data set and we will sample with replacement a subset of data points and feed this curve to this this subset of data. Then we go back and again sample with replacement and feed the curve and so on. If the data have little variability, every time we repeat it, the curves should be very similar. If the data have a lot of variability, depending on what gets sampled, the pattern of the curves would be quite different. And this is an example here. So the gray lines, these are different instances of fitted, this hockey stick patterns that we have to the resampled data. And by the way, sometimes if we cannot find a change point, we say, okay, it's linear, so we just fit a straight line. Meaning that if the data are entirely in the linear portion of the dynamic range, it's just linear. So this shift only occurs when it's necessary in the data. And so what you see now in this particular case, I'm only zooming in into low concentrations, but you see there's quite a bit of variability in the location of these gray lines. And what we will do now, we'll actually average over all of these gray lines. And you see that the average is exactly this characteristic nonlinear pattern which we see in the apparent calibration curves. So now we explicitly show that this flattening out is the result of our uncertainty in the location of the change point in the canonical calibration curve. And you see that if we now zoom out to the full range of concentrations, well, it's actually quite linear as expected in the full range, but it will be flattening out in the low abundance range. Well, so that's what we do. Here's some examples. So this is what a logistic fit would look like versus our proposed fit. So we argue that this is a better quality fit. But importantly, because the fit is different and better quality, what it turns out is that frequently it leads to estimates of the figure of merit, which I just defined, which are larger than the estimates based on the existing methods. Meaning that the existing methods, when they don't fit well, they are too optimistic and they give us limits of detection lower than what they really are. And we think that it's quite dangerous. And so we argue that these are more realistic estimates of the figures of merit than estimates based on linear regression. Now, how do we know this? Well, in statistics, we don't really know the true answer, so we simulate the data. We simulated something which has this pattern of flattening out. And you see that straight line, when it fits, it kind of gets attracted by these points. And clearly the prediction interval will be too small. This is why the limits of detection are too small. Now, what we propose fits data well, and now we actually can look, because we know the true answer. We compare linear and logistic, and our approach, again, I called proposed, sorry. It's a little bit conservative, but much more close to the true value than the existing methods. And now the most important, we actually took a collection of data sets, of calibration experiment data sets from the CPTAC portal and several others, from collaborations, including collaboration with Andy and collaboration with the McCoss lab. And we don't really know the answer for these experimental data sets, but what we can do, we can plot the ratio of figures of merit by our method versus by straight line. And if the ratio is greater than 1, it means that our results are more conservative. And what we also do, we annotate here how often in this data set the peptides had this flattening out pattern. And so what you see is that if this flattening out pattern is small, like for example here, 7%, our approach is pretty much identical to the calibration by the straight line. Here is 14%, also very close to the calibration by the straight line. But in other cases, when we have 80% of peptides have this flattening out pattern, our results are more conservative than the straight line. So it does make a difference when we do this large-scale calibration, and the same thing is for limits of detection. Well, I think it means that we have to be very careful when we start doing assay characterization on a large scale to make sure that we accommodate this type of patterns. Okay, and this is part of MStats. It's implemented. I don't think we will be okay, maybe, yeah, but it's implemented.
Everything to do it if we've got time.
Okay, so but that's available if you would like. And okay, let me make sure I leave enough time to Lindsay. Let me just very quickly show you the last part. You can ask me questions after that during the day today if you would like. So the last part is talking about system suitability and quality control and longitudinal monitoring. So I hope by now you see that a lot of motivation for our work is reproducible research, right? And trying to understand how to eliminate artifacts of random variation from systematic changes. And quality control and system suitability is a really big part of that. So the difference, by the way, between system suitability and quality control, system suitability is something which you determine before you run the experiments. Is your system suitable for work? And quality control is while you collect the data. So are my data good quality? So these are two different procedures, but the common thing with them is that they're all longitudinal. So you collect data in both cases while you run the experiments. So let me first show you what we propose. This is also a collaboration we have with the Skyline team for quite a while. And what we offered is statistical methodology, which is state-of-the-art in the statistical process control literature. And what you would typically do, you would look at a peptide, which is a control peptide or standard peptide, and you would have some metrics from this peptide, such as peak area, retention time, I don't know, other things, peak asymmetry, and so on. And you would systematically profile this either as part of system suitability or as part of quality control. And here is an example. This is the time. This is the metric itself, for example, peak area for this particular peptide. And you have some runs. Essentially, you want to make sure that they are within the limits. And you can have a guide set of what you decided are good quality runs. You learn the variation of this metric. You establish the limits based on this metric, and then if the measurements exceed this metric, then it's essentially a red flag, right? You say something is wrong. And this is a very traditional thing that people use. What you can also do is the Z-chart. So again, signal to noise, right? Instead of just looking at the peak area, you have the peak area divided by its variability, because then the limits, they're all the same for all peptides. So it's also kind of easy to see. And you see that you can easily diagnose some individual deviations. But these are the shifts in the mean. So what we also proposed is that sometimes the problems occur not because you have the shift in the mean, but shift in variability. For example, retention time on average stays the same, but it becomes more and more variable. So you want to be able to notice this type of thing. So this will be another type of summary of the data, which is called moving average or MR chart or moving range. And now you can also find the deviations in variability in time, just like you could find the deviations in the mean. But the problem with these methods is that they can only find really large effects. What if you don't have like a big change, but small but sustained drifts? This type of methods are actually not good at that. They don't diagnose small sustained drifts. You have other types of metrics, and so this is another example. So it's called cumulative sums, and they can diagnose systematic drifts in the mean or in the variability of different metrics. And you can also have the control limits, and it will show you when you are your peptides are out of control. These are all useful things, but you can probably imagine very quickly that if we have many peptides, and for each peptide we have many metrics like peak area, retention time, whatnot, and for each metric we can have problems with mean, with variability, big shifts, sustained drifts, and so on. A variety of charts which you can produce, and they're all kind of very hard to summarize. So what we do also in MStats, we propose summaries where we call them decision map. So essentially it's a pass-fail criteria here for the mean, and this is for the variability, peak area or retention time. If over all the peptides it looks good, it's in blue. If some proportion of peptides fails, it's in orange, and if a larger percentage of peptides fails, it's in red. So you can kind of follow all of these metrics systematically and look for the problems. Now, if problems start appearing, you can kind of look a little bit more in detail. So here we call them river plots. They're focusing on runs. Here the x-axis is time, and the y-axis is the percentage of peptides which have either increase in the mean or decrease in the mean, increase in the variance, decrease in the variance. And you can see, for example, here at this time point, 50% of peptides start having increase in the retention time. So now you say, okay, something is not quite right. But the interesting thing here is this type of charts also allow you to pinpoint the time when the change started to occur. And this time is different for different peptides, so those red dots here, they indicate the potential starting time points when the problems begin to occur. So this is run-centric and this is peptide-centric, so you can see now for different peptides what type of problems they have. And you see that some peptides never had any problems, so the colored areas are staying in the center. But peptides which have colored areas at the outside, it means that in many runs, these particular peptides had problems. So you can kind of overview your whole calibration, your QC experiment in these plots, and then you can dig into the individual charts if necessary. And so I know that you have discussed already the Panorama, AutoQC, and others, so this is just a small summary of like different functionalities available in every tool. So as Prokop was the first kind of precursor to all of this work, it's available as an external tool in Skyline. It only has X charts, so detect large shifts in the mean. Panorama AutoQC has implemented many of the things which I just kind of discussed, so looking at the variability and sustained drifts in mean and the variance. And then in MS Stats, we have a graphical user interface for this, but we also have a command line version. We can provide the change points, so times when the problem started to occur, and also the summaries with the river and radar plots. So this is, usually we don't do much graphical user interface, but here we actually have a web browser interface where you can just upload your QC data. And there's more information here in this manuscript. Okay, so I'm finishing right on time. I just need to thank a lot of people. So a lot of this work was done by my group members who are here, especially Mina Choi here in the background. She is the leader of the MS Stats effort. The assay calibration is done by Cyril. Tsung Heng has done a lot of work related to MS Stats and also in documentation. Ting is also part of the MS Stats team. A lot of this work was motivated by collaborations with the Abersold Lab at ETH and of course with Mike and Brandon's groups. I think it was really, really important. It is, and hopefully will be, important interaction for us. And we also have additional collaborators who helped us in various aspects of method development. So, I will probably stop here to make sure that Lindsay has the time she needs, but I'm not going away. I'm staying in the back. If you'd like to talk to me, please don't hesitate. Okay? Thank you very much.